is a nice long review article. Unfortunately, I'm going to be brief about it, even though even being brief may take two podcasts. It's worth reading if you are interested in this topic of AI for modeling and understanding extreme weather and climate events. Obviously, it looks at climate event detection, attribution, modeling, understanding processes, data issues, data use issues in terms of privacy, copyrights, and then ethics of AI, all those details, which I'm not going to read all of it. So let's read the abstract and then read whatever I picked as the most salient points. In recent years, artificial intelligence has deeply impacted various fields, including Earth system sciences, by improving weather forecasting, model emulation, parameter estimation, and the prediction of extreme events. I have discussed these issues already in this series on AI and climate. The latter, the prediction of extreme event, comes with specific challenges such as developing accurate predictors from noisy, heterogeneous, small sample sizes, and data with limited annotations. So that is a separate section in the paper that I'm not going to read. This paper reviews how AI is being used to analyze extreme climate events like floods, droughts, wildfires, and heat waves, highlighting the importance of creating accurate, transparent, and reliable AI models. We discuss the hurdles of dealing with limited data, integrating real-time information, and deploying understandable models, all crucial steps for gaining stakeholder trust and meeting regulatory needs. I've already discussed interpretable and explainable models, AI models, whether they are a black box or you understand what it's doing. So that's also part of this understandable models. We provide an overview of how AI can help identify and explain extreme events more effectively, improving disaster response and communication. We emphasize the need for collaboration across different fields to create AI solutions that are practical, understandable, and trustworthy to enhance disaster readiness and risk reduction. Right? Understanding is of course very useful for even building dynamic models and improving predictions from dynamic models, but AI can give you a leg up in terms of giving very quick forecasts, early warnings, compared to dynamic models, which can take a lot of time to run. If you want a 15-minute warning, running a model has to be much faster, maybe 1 minute, but that's almost never possible. So AI can help there as well. The frequency, intensity, and duration, so I'm jumping ahead. The frequency, intensity, and duration of climate extremes have increased in recent years, posing unprecedented challenges to societal stability, economic security, biodiversity loss, and ecological integrity. These events, ranging from severe storms and floods to droughts and heat waves, exert profound impacts on human livelihoods and the natural environment, often with long-lasting and sometimes irreversible consequences. Modeling, characterizing, and understanding extreme events is key to advancing mitigation and adaptation strategies as well. So that's a longer time action than early warnings. Providing a precise, formal, a universally applicable definition of an extreme event is inherently difficult, so I've jumped ahead again. Statistical definitions that define extremes as the tails of a probability distribution, such as 1% or 5% of the distribution, are often insufficient, as they may fail to account for complex multidimensional interdependencies, such as changes in societal and geographic context and the cumulative nature of the impact. So 95th percentile, 99th percentile of temperatures and precipitation, etc. are typically used, but then there are lots of debates about the definitions elsewhere as well. In this context, AI has emerged as a transformative tool for detection, forecasting, analysis of extreme events, and generation of worst-case events, and promises advances in attribution studies, explanation, and communication of risk. Attribution is where you go back and see if the event was made worse by human actions such as increased greenhouse gases, global warming, land use change, etc. The capabilities of machine learning and deep learning, in particular in combination with computer vision techniques, are advancing the detection and localization of events by exploiting climate data such as reanalysis and observations. So all these technical terms like machine learning and deep learning I have described elsewhere in the podcast in this series, and detection and attribution also I have discussed elsewhere. Modern techniques for quantifying uncertainty are necessary to progress in climate change risk assessment. Using ensembles in combination with AI models has progressed the field of attribution of extremes, identification of patterns, trends, and climate analogs. So ensembles basically means you make multiple realizations with an AI model or some other way, so that Mother Nature takes one track, but she has the potential to take many other tracks around it based on the initial conditions and some details you can look up elsewhere in the modeling section and so on. Yet, AI does not only excel at prediction but also can explain processes such as explainable via explainable AI, XAI, and causal inferences, which is essential for decision making and effective mitigation strategies. Recent advances in large language models that retrieve information from heterogeneous text sources allow for effective integration of methods for communication tasks and human-machine interaction in situation analysis. Okay, that's kind of the introduction part. Let's look at some figures. We'll look at more text as well. This is a general artificial intelligence driven extreme event analysis pipeline. So you have data collection and analysis, and there is always historical data as well that will inform data collection and processing or pre-processing once you apply the methodologies and look at outputs and identify gaps and needs and so on. So weather and climate data reanalysis is a blend of models and data which reconstructs historical data as a filled, you fill the gaps in space and time with the model used. It's like a dynamic interpolation in some sense. And you have direct observations from satellites, in situ, balloons, aircraft, ships, and autonomous buoys and so on. You have some pre-processing like detrending, denoising, and gap filling. These are very generic terms, but they are basically involved in the analysis before you feed it to AI methodologies where there is a modeling. So machine learning and computer vision give you understanding with explainable AI and causal inferences, and there is an integration with natural language processing. Very general terms, but still very critical in how these things work. And then you get outputs such as predictions, patterns and trends, causal relations, and attributions, how humans are affecting these as well. Okay, so then we can redefine hypotheses and model improvement and adaptation to go back and reiterate on these things. And you do quick forecast. This is already done beforehand with the historical data, so that you get near real-time data and make forecasts of wildfires, heat waves, floods, and droughts. Droughts don't usually need 15-minute forecasts, but nonetheless, you have flash droughts now which need a few days or few weeks forecasts. This is a detailed table, so I've split it. Comprehensive categorization of extreme event analysis. We are looking at data, modeling, understanding, and trustworthiness, and last mile. So you'll have to remember these for the next page. We are looking at aspects like data collection, harmonization, pre-processing, feature selection, extraction, simulation of extremes. Then in modeling you have detection, prediction, impact assessment, and understanding and trustworthiness. Again, explainability, causality, extreme event attribution, uncertainty, quantification, and last mile issues like operationalization of the system to issue actual advisories, alerts, and strategy decision backups or support, communication of risks and ethical aspects of how we use the tools and the data that go into them, because often you have socioeconomics and people's information, and of course policy and decision making. So data modeling, understanding and trustworthiness, and last mile then relate to tasks, standard methods, and current AI methods. Am I going to read all these? Not really, but let's read the top one and maybe the bottom one as examples. Gather, standardize, and clean relevant multi-source data for the downstream task. In standard methods, you have manual normalization and detrending, statistical methods for denoising, gap filling, and data fusion. Whereas in current AI methods, you have automated ML, DL, machine learning, deep learning based pipelines for denoising, gap filling, and data fusion, anomaly detection, etc. So you have simulating extremes, detection and identifying extreme events, estimating effects of extreme events on society, making rationale of a black box ML method. So black box is where you feed in something, something comes out that you have to know somehow is reliably useful, usable, but you don't know exactly what the model did. Explainable is where you understand what actually went on in the analysis for the results that it produced. Quantifying the influence of anthropogenic forcings on extreme events, so that's kind of attribution on how probability of the event changed because of anthropogenic forcings. Reading the last one, manage and mitigate impacts of extreme events, ensuring resilience and safety. That's the last mile issue. Risk assessment management, cost benefit analysis, multi-criteria decision analysis, adaptive management, and community-based participatory approaches are the standard methods that have been used explicitly or implicitly. But with AI, you have time series analysis, ensemble methods, anomaly detection, clustering, reinforcement learning. Wow, doesn't translate immediately to understanding in simple words, but the idea is that AI will improve on standard methods by adding value, speed, accuracy, and reliability, and also allow people to participate, crowdsourcing of data, etc. Another complicated figure coming up, but mostly schematic. It's components in an artificial intelligence pipeline for extreme events again, but now we are looking at specific steps: detection, forecasting, and impact assessment. Detection, is this anomalous and extreme? So that you have a time series of variables, you have a AI/ML model, and there is an anomaly score at time t0. Forecasting, then what will happen in the future? So you use variables until time t for training the model, and then anomaly score in time greater than t0. So you progress in time, integrate forward, but in AI it's mostly about you can still call it integration. It depends on whether you are combining dynamic models or just purely going from data to AI model to forecasts, but often variables until time t may come from the model itself, model forecasts, okay, other than historical training. Impact assessment, how much foreseen impact? Anomaly intensity at t0, then the model takes you to impact estimation at t0. Understanding and trustworthiness is the next step. Explainable AI, what are the main drivers? Interpretable by design, so the model is built to be able to be understood as to what it's doing. Feature attribution, distillation, and contrastive and counterfactuals. Counterfactuals is where you say without human impact it would have gone here, but because of human impact it went there. So the counterfactual world is where you have somehow removed the human impact, or it could be also where heat wave and a drought occur together, and then you can remove the drought and look at the heat wave, or remove the heat wave and look at the drought. So counterfactuals are basically where you are looking for what if this didn't happen, how would this other thing would have changed. Causality and attribution, why and what if. Counterfactual, so what would have happened if and why. Intervention, what happens if I manipulate this and how, so you can develop adaptive or mitigative or disaster management scenarios by doing these kind of intervention scenarios. Causal discovery, what causal structure explains this, which is important for understanding and improving the AI itself, as well as process models, dynamic models. Uncertainty quantification, how sure are we? So you have to start with quantification, go to predictive and propagation. So there are aleatoric and epistemic uncertainties, which means random errors versus errors arising from missing understanding, let's say, okay? Something that's maybe not even captured in data, but even with enough data, you can have random uncertainties, random errors growing or not, depending on various feedbacks. For example, a drought can exacerbate a heat wave, right? So communication, operationalization, so accountable and robust results. You can go from managing uncertainty to accountable results to trustworthy results and automated integration, so that the decisions are coming with information that's gone through these steps, so that you are able to operationalize your disaster management, risk management, etc. Risks and ethics, accountable and robust results again. So here you have language, large language models and bots which can synthesize information. You have to take data from various sources coming at you in large sizes and at very rapidly, with things changing fast, but you have to produce patterns and information in small bites that can be used in decision making on the street as a last mile action. So situation rooms and panels do that, but you have to get information including risks and ethics. The decision maker cannot keep worrying about the ethics of everything that happened before. He has to make decisions, he or she has to make decisions because the lives and livelihoods and infrastructure and properties depend on it. Fair machine learning models, so it's kind of a discussion, debate that goes on. Bias, ethics and guidelines. So if AI is built without worrying about biases and ethics, when you make decisions, you may allocate resources to places which are rich. Some ethnicities may get neglected, or some religions may get neglected, and so on. So bias and ethics and fair machine learning models are very critical, because this is already beginning to play out. Okay, in communication for policy and decision making, you need analysis to action. So you need reinforcement learning, participatory human-machine interactions, multi-criteria analysis, socioeconomic, environmental, biodiversity, and vulnerabilities, etc. And risk assessment as a whole, you want a risk map so that you have identified levers to reduce vulnerabilities, exposures, response times, and hazards. Often you can't reduce, but you can mitigate them, like urban heat can be mitigated by urban forests or green roofs and various other measures. So they all have to come together. So extreme, I don't know how many pages more. I have lots of material, so let me go for a few more minutes on this first one. Extreme events understanding and trustworthiness. Yet all previous approaches, so I have jumped ahead, focus on what, when and where questions, not the why, what if and how confident ones, which means AI has been used to train with data and to focus on extreme event detection, forecasting, maybe attribution, but not so much causal understandings and what if scenarios of what actions could have prevented the extremes or its impacts, and how confident we are on these forecasts or understandings. The latter questions are essential for achieving trustworthy ML as high stakes decisions impacting public safety, health, infrastructure, and resource allocation depend on it. Disciplines like XAI, explainable AI, and uncertainty quantification offer methods to make AI more reliable and trustworthy. So we'll look at the figure, but there is more details here on reliability, trustworthiness, uncertainty quantification that I'm not going to read. These approaches not only help us interpret AI model predictions, but also enhance our understanding of extreme events themselves so that dynamic models can also be advanced in the meantime. Techniques such as causal inferences and extreme event attributions further complement explainable AI and uncertainty quantification by understanding the mechanisms behind these events, crucial for improving AI models and gaining trust in the decision-making process. Explainable AI then, many models are transparent and interpretable by design, like linear models or decision trees. Still, they may not perform well on complex problems and are rarely employed in extreme events. We'll looked at the table already in existing standard methods. Explainable AI aims to unveil the decision-making process of AI models. XAI, explainable AI, also facilitates debugging, improving models, and gathering scientific insight by revealing the model functioning, learned relationships, and biases. Improving the AI models itself is important, and if it's an explainable model, it's easier to do that because it's a black box model, then you may be just scratching your head as to what it's doing. Okay, and then there are sometimes black box models run, and a simpler explaining model is also associated with it, but the issue of improving the model itself still comes back to knowing what it's doing. The most commonly used XAI approaches rely on model agnostic distillation or feature attribution methods, rely on model, I repeated that, distillation methods such as shapely additive explanations and local interpretable model agnostic explanations, creating surrogate models, and have been widely used in geoscience and climate sciences. So we are talking about AI applications, especially here in weather and climate, and that too in extreme cases. Feature attribution methods like partial dependence plot or gradient based class activation map highlight important features by perturbing the inputs or using backpropagation. Recent approaches explain DL models using attention in drought prediction and prototypes for explaining event localization. When you get data, you have to precisely pinpoint where the extreme event happened or the impacts happened. XAI has also been used to evaluate climate predictions and thus offers an agnostic data-driven approach for model data intercomparison. Nevertheless, most XAI methods, particularly post hoc approaches, approximate the underlying model, and the lack of a clear definition for a sufficient explanation complicates their evaluation. Further discussions on XAI limitations is available in Model Challenges, which I'm not going to read in detail, but I wanted to get a sense of the issues that we are dealing with when we take AI for understanding and explaining extreme events, understanding their impacts, localization, uncertainties, and is able to predict them as well as provide longer term information for policy and decision making. Okay, so maybe I can leave this first podcast here and continue in the next one. This is almost 23 minutes, but you get the idea. We'll complete hopefully in the next podcast, but the paper is long and it's a review article, so it comes with incredibly useful list of references that you may want to follow up if this topic is of particular interest for you. And the sections are nicely divided into modeling issues, data issues, ethics issues, and reliability, explainability, etc. Okay, see you in the next part of this topic.